This meeting is being recorded.
In problem 21 from chapter 15, we're asked here how we could use NMR spectroscopy to distinguish between the following compounds. So we have sets here from A through F, and generally we can determine if they have a different number of signals. But sometimes if they have the same amount of signals, then we'll have to look a little deeper. So let's take a look here in group A. The first compound will exhibit symmetry, so we should only see one signal here for these two protons, second signal here for these two, and then a third signal here for these two. So a total of 3 signals, whereas compound 2 here, this does not have that symmetry, so we would actually see 1, 2, 3, 4, 5, 6 signals for this compound here. So that's how we could differentiate between these two. They have a different number of signals. When we move over to the 2 compounds in B here, so both of their proton and Mars spectra will have 2 singlets. So we have 3 protons here, and then we have 3 on each of these. So we have 1 singlet here, and then 1 singlet for these 9 protons. So since we have 3 to 9, and we have the same number of signals, we have to kind of look further into their integration. So we're going to have 1 to 3 ratio for both of these compounds. So we actually have to look at the location of these 2 signals. So again, we have this 1 to 3 ratio. So this signal for these protons over here, these are alpha to a carbonyl, right? So they're alpha to this C-double-O bond here. So we should see a signal approximately 2 ppm for these, since they're methyl plus 1. And then in the second compound, the singlet over here with the smaller integration value, this is now alpha to an oxygen of an ester. So if you recall, that would add about 3. So we should see a shift for these lower integration value, these 3 protons here, around 4 ppm, because we add 3 plus that 0.9. So that's how you would be able to differentiate between those 2 compounds. But again, first look for different number of signals, and then if they have the same ratio, the same integration values, then you might have to look for a shift as a last resort. Now with compound C, it's a little bit easier. We're going to see 1 signal here, 2 signals. The second signal there for compound C, right? We have symmetry. We also have symmetry with the second compound here, but we're going to see 1 signal for these protons, a second signal here, and then a third signal down here. So different number of signals. Then we have compound D here. So again, this is just easier to distinguish between the different number of signals. So we have some symmetry over here. So we're going to see 1, 2, 3, 4, 5 distinct signals here, whereas we're only going to see 1, 2, 3 signals with this compound here. All right, so now we go to compound E, and the first compound here will exhibit symmetry, so we're only going to see 2 signals. So we have 1 signal here, and then second signal here. Whereas this second compound here, we're going to have a total of 4 signals. So we have 4 signals over here, only 2 over here. So once again, differing number of signals. Last but not least, we'll have the first compound will only have 1 signal here. All of these methyl protons are equivalent. 1, 2, 3, 1, 2, 3. So all 12 of these produce that 1 signal. And then we have second signal produced over here. So these 3 methyl protons would produce the first signal, and then this proton here would be the second signal. So again, with compound F, we can compare. We have 1 signal versus 2 signals.